that exist on this line called 2x1 plus 3x2 equals 19. So if I have two dots on a line, it's a pretty easy thing to graph that line. Okay? So let's find this first dot. Here's the first set of coordinates right here. We know that this point where x1 equals 0 and x2 equals 6 1/3, that dot exists on this particular line. Okay? The second dot where x2 equals 0 and x1 equals 9 1/2, we know that's another point on that line. And so if I put those two dots, if I graph them and then connect the dots, I've graphed the line. So it's that simple. So I need to label my axes so that I can identify where these dots are. So let's just graph or rather label some of these points. I'm trying to be careful. If you have graph paper, grab it. But otherwise, try to be real careful to keep your axes straighter than I did, and try and be careful to keep the distance between your labels roughly equal. Okay? Getting kind of, that's supposed to be one dot. Okay, so this is maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And similarly, I'll do the same for the vertical axis. 1, 2, whoops. I need to move this, open this up a little bit, give myself a little more room. Okay, I'm back. I've redrawn the axes because I got a little sloppy there with the smartboard. And what I'm going to do now is I'm going to take the coordinates from this second constraint, and I'm going to plot those 2 points. The first point is where x1, which recall x1 is my what's going on now? Okay, x1 and x2. So where x1 equals 0, that's this vertical axis, x2 equals 6 1/3, which is going to be about right there. Okay? And then where x2 equals 0, that's the horizontal axis, x1 equals 9 1/2, which is right there, approximately. And then I'm going to connect the dots here. Okay? And every dot on that line satisfies this equation, 2x1 plus 3x2 equals 19. Notice I said equals. Notice I said equals. Every dot on this line satisfies the equation, 2x1 plus 3x2 equals 19. The constraint, however, says less than or equal to 19. So what this constraint is referring to is every dot within the triangle you see here. Okay, every dot to the left of that line. Okay, so let's test it out. Here's a set of coordinates right here, 0, 0 down here in the corner, and let's see if that is true. If I take x1 equals 0, x2 equals 0, is that constraint satisfied? And that would be 2 times 0 plus 3 times 0 is less than or equal to 19. That's true. 0 plus 0 is less than or equal to 19. If I take coordinates outside of that area, let's say out here where 5 equals, or x1 equals 5 and so does x2, approximately right there, then that should not satisfy that constraint, and we'll find that it does not. So 2 times 5 plus 3 times 5, is that less than or equal to 19? And you'll realize no. 10 plus 15 is 25, which is not less than or equal to 19. So the constraint, again, corresponds to the area below or to the left of that line we just drew. Of course, we have those non-negativity constraints. The constraint that is x1 must be greater than or equal to 0 essentially ensures that we're to the right of the vertical axis. And the constraint that says x2 must be greater than or equal to 0 ensures that we're above the horizontal axis. So at the present time, we know that our solution has to be in this triangle we see here. But let's now graph that first constraint. The first constraint says that x1 must be less than or equal to 6. And as we discussed earlier, that means that our solution has to be to the left of that line. If you look at that and you do the same thing we did, you say instead of less than or equal to 6, you say x1 has to equal 6. That's the line we graphed. And then if you just realize that we're talking about everything to the left of that line, then you've captured this less than part. So right now our feasible solution space is in this, this area in kind of in the corner of what we've graphed here. We still have to graph the third constraint, which says that x1 plus x2 equals 8, or actually less than or equal to 8. I'm going to do the same thing I did for the second constraint now, and I'm going to do the little t, and I'm going to set one equal to 0 and solve for the other. You can do this in your head, but let's go ahead and go through the process. So if x1 is 0 with respect to this third constraint, what will x2 have to equal? So what you're saying is 0 plus something has to equal 8. Well, of course, that's 8. Okay? And x2, we'll set that equal to 0, and we'll solve for x1. Of course, x1 plus 0 has to equal 8. Well, of course, 8 is the answer there. So we get this set of coordinates that is 8, 8. Okay? And more specifically, we're at the 8 on either axis. So where x1 equals 0 and 8, or x2 equals 8, that's this setup here on the vertical axis. And where x1 equals, let's see, I'm sorry, x1 equals 8 and x2 equals 0, that's this spot down here. Okay? Okay, so now let's graph that line. And I'm going to come, oops. What? Fun with smartboards. I somehow moved my dot. That's not good. Okay. We're going to come right through here. And that's my third constraint. The x1 plus x2 equals 8. And again, it's a less than or equal to constraint, so it's referring to everything to the left of that line. Now, it's not enough to satisfy one constraint. It's not enough to satisfy two constraints. You have to satisfy all constraints, and if we find the area that satisfies all three of the constraints, it's this area that I'm shading right here. Okay? So if you think about it, each of my constraints is satisfied anywhere in that shaded area. So if I wanted to choose the solution, say, x1 equals 2 and x2 equals 2, that's this dot right about here, that's feasible. I know that'll work. I won't violate any constraints. What that might mean in the real world is I have plenty of resources to do that, or there's plenty of demand for my product to do that, or all of the above. Okay? But if I wanted a solution that existed out here, you know that's not going to work. This dot out here where x1 equals 8 and x2 equals 6, because that's violating, well, all of my constraints. So we have just defined what we call the feasible solution space. And the next step will be to actually find the optimal solution point. So we've defined what's possible. Now we want to figure out what is optimal. Well, if you think about something, I think it'll be intuitive. Think about a field, okay, and think of these constraints as kind of the fences. Is it kind of intuitive that the optimal solution will not be in the middle of the field? It'll be in one of the corners. In other words, if these constraints are what are keeping me from perhaps making more money or increasing revenues, isn't it intuitive that you would push these constraints as far as they would go? In other words, you would be on the fence. You would push it as far as it would go. Well, it turns out that intuition is correct, and your optimal solution will always be at what we call a corner point. Okay? Your optimal solution will always be in one of these corner points. And you can go through and you can do a brute force method of solving the coordinates of each of these corner points and plugging them into your objective function and figuring out which one yields the highest value. So, for example, we know that this coordinate right here where x1 equals 0 and x2 equals 6, we know x1 equals 0, x2 equals 6, and we know if we chose that solution that our profit would be 5 times 0 plus 6 plus 7 times 6. So the profit would be 42. What have I done? I've plugged the coordinates of that dot into my objective function. Okay. Similarly, if I chose this solution down here where x1 equals 6 and x2 equals 0, then this point right here, we know the profit down there would be 5 times 6 plus 7 times 0, or 30. So we know automatically that this solution up here on the vertical axis is superior to this one down here. We're still not so sure about this solution or this possible solution. I'm pretty sure this corner point down here in the bottom left is not optimal because it yields 0 profit. But these are our corner points, and we know one of those will be the optimal solution. Okay? There's kind of a shortcut to figuring out exactly which of those points is the optimal,